Okay, the first way we can improve on the previous solution is to use an abstract class. Abstract classes are classes that you cannot directly instantiate. In other words, you can't call new on the abstract class, but you can subclass it, and then you can call new, you can instantiate the subclasses. In abstract classes, you can mark certain methods as abstract. Those methods must be implemented by all the child classes, unless they're also abstract classes. Otherwise, the code won't compile. So here's an example. If I mark a class as abstract, then it's not possible, it's not legal, it won't even compile if you try to call new directly on this class. Furthermore, I can mark some of the methods as abstract. If I mark a method with abstract, then I just put a semicolon, not curly braces, and a body. So in other words, I've given a method specification, public, abstract, string, get message, parentheses, semicolon, but I haven't actually said how it's going to be implemented. It'll be up to the child class to say how it's implemented. But abstract classes can also have regular methods that are declared just like we did in normal classes, and those will be inherited just as we discussed in normal inheritance in the previous lecture. So you can mark a class as abstract. It cannot be directly instantiated, and you can mark methods as abstract. Put a semicolon at the end, no method body, and those methods will be required to have concrete implementations in the child classes. Okay, why is this idea useful? Well, the general idea is that it enforces behavior. In particular, unlike our previous example, using an abstract class guarantees that all classes will have certain methods. In fact, it guarantees that they implement certain methods, they don't just inherit them. It allows you to handle collections of mixed but related types, but in a neater way than in our previous example where the parent class was a normal class. And finally, just as with the previous solution, it makes sure that methods that handle mixed types will still work in the future when new types are defined. And the way that it can guarantee this is because you know ahead of time that all future subclasses will have the appropriate method and will have their own specific implementation of that method. All right, let's use abstract classes to try an even better attempt at making a static method that can take an array of mixed shapes and sum up their areas. So the difference from the previous solution is that our shape class will now be an abstract class. Inside the shape class, we'll give the specification for a getArea method. In other words, this is what a getArea method will look like. Here's its return type and method argument signature, but I won't actually give the definition. This means that shape cannot be instantiated directly, and this also means that subclasses are required to give their own implementation of the getArea method. The rest of the approach will be the same. We'll have all shapes extend this class, but now they can't forget. They must give a more specific definition of getArea. As before, we will make a shape array, but the things that we'll put in the shape array will not directly be shapes, they'll indirectly be shapes. They'll be circles, rectangles, and squares, and so forth. We'll pass that to our static method, some areas as before, and some areas will look exactly the same as it did before. It'll take an array of shapes, loop down, call getArea on each one, and add up the total. So the big difference is the parent class. It'll now be an abstract class. It'll have an abstract method, which means it's just a method specification, not a method implementation. It just says all subclasses will have a method called getArea that takes no arguments and returns a double. But it's up to the subclasses to give the actual implementation, and they can't forget. If they extend a shape, unless they're an abstract class themselves, and they don't give a definition of getArea, the code won't even compile. And then I will extend shape for circle and rectangle as before. I'll extend rectangle for square as before. And I will make my shape array containing a mixed set of shapes as before. I'll pass it to the static method as before. And the static method will be exactly the same as it was before. It'll take an array of shapes. It'll loop down each one and call getArea and total it up. That's safe because Java knows at compile time that all shapes have getAreas, and it'll return the sum. All right, this is an excellent solution. And in fact, up through Java 7, this was the best solution. However, in Java 8, Interfaces are even more flexible than they were in Java 7. And as we'll see in the next section, you can implement more than one interface, but you can't directly extend more than one class, whether it be an abstract class or otherwise. And so since our abstract shape class didn't have any instance variables, it actually would be slightly more flexible in this case to use an interface rather than an abstract class. And in fact, that's a general principle. Starting in Java 8, interfaces can do almost everything abstract classes could have done in earlier Java versions, and so the role of abstract classes is diminished relative to Java 7 and Java 8. In particular, abstract classes are normally in Java 8 now used only when you need, in addition to abstract methods, you also need instance variables in the parent class.